Good evening, Earthling. The first simulation shows a small star in orbit around the Sun going nova. The debris begins to form a primitive solar system with angular momentum in a uniform direction. The orbits are fairly close to being circular. We can set the autoclear here so that the orbit lines get refreshed every 5 seconds. A 100 years later, of the 500 planets that resulted from the nova, we can see that only 5 remain here. The rest have either combined, exited the screen, or impacted the Sun. The screen represents space that is within the orbit of Uranus. But because Newtonian gravity structures are identical in a wide variety of scales, all that matters is the shape. So we have a roughly circular solar system after quite a short time. 1 second is equal to 1 virtual year, here. The next example shows planets that have formed from random origins. Gravity contracts the system, and the Sun initially only absorbs those fated to die. You may notice that planets in opposing directions neutralize each other's momentum, and thus also are swallowed by the Sun. These early stages are quite chaotic, and popular theory suggests that the interacting gravity fields would cause the orbits to circularize. But after several millennia, the orbits are almost never circular, and if they do become circular, then they soon get distorted and eccentric. The bodies are of low mass, and thus have very little effect on one another, so the process is far slower than in the nova scenario. So I pause the simulation and give this planet here the mass of Jupiter. We can flip through the other planets and see that they have absorbed very little mass. Note that the simulation uses units that are set as 1 equals Jupiter's mass. Now notice how the massive planet dents the orbit of the blue planet, here. Then a very rare event luckily occurs. The big planet catches a moon. See here. But the orbit of the moon gets distorted as the planet nears the Sun, and the moon is soon lost. This is a typical result, and it shows that the orbits of moons could not have a random origin. This is because random interactions are exponentially more likely to destroy a lunar orbit than they are to cause one, when the planetary origins are random. Let us try this type of scenario again. Notice that there is always deliberate randomness in the algorithm, so no two scenarios are ever identical. Bear in mind that one needs to run many scenarios for very long times to really see the patterns yourself. But random origins overwhelmingly cause eccentricity in the orbits, not circularity. The truly interesting part is that the time frame for orbits forming is still shorter than commonly expected regardless of origin. It's just a matter of centuries, not millions or billions of years. So to see it form in the real cosmos would be exquisitely rare. And to be quite frank, if you are not constructing such evolutionary gravity models yourself, then you really just do not properly comprehend the math of gravity and astrophysics. They are not all that hard to build. Let's try a nova event again. These models only try to show how the orbits of Jupiter and Saturn can form. Planets like Uranus and Neptune would be outside the screen, whilst the inner planets can actually only be lost moons of Jupiter. But that is revealed in the Orbit Game 5 EXE algorithm, and another story entirely. This model only shows Newtonian gravity, whereas Einstein's formulae are described in the algorithms Orbit Gravity Sim 11 EXE and Orbit Gravity Sim 12 EXE, and that is less a story and more a fairy tale. These two planets' masses are now nicely similar to Jupiter and Saturn. See here and here. Their orbits have structure much more circular than the scenarios with the random origin. I am currently exploring the algorithm Orbit Gravity Sim 14 EXE. It functions fine and describes similar details but in 3D. Those results and their algorithm will be published in time, but the introduction of the z-axis just emphasizes the same conclusions. Orbit Gravity Sim 15.exe is also functioning and details our own solar system in 3D, but strictly according to evolutionary gravity. Those results will be available later this year, 2019.